Hi everyone, welcome to week 10 of incomplete data analysis, and in this week we will cover what was left from last week, and it is multiple imputation for the case where we have several variables with missing values. We will start with an overview of the methodological concepts, and then we will have a tutorial on R about how to use mice for the case of multivariate missingness. And okay, last week we covered the case of multivariate imputation for univariate missingness, and we have seen that the package mice has several options available for imputation when the variable is continuous, right? We can use a normal linear model, the Bayesian version, or the frequentist counterpart based on bootstrap. We can use predictive mean matching. I have not mentioned it, but there are another couple of methods available based on random forests and trees. And then if the variable is binary, a logistic regression model will be used for imputing the values of the binary variable, and there are also functions available for the case where the response is categorical or categorical with the levels order or unordered, and we have covered in some detail these options. In this week, what we will be learning is what mice does, or what are the options available when several variables have missing values. And if you remember, if we go back to week 4, we have superficially touched this issue when we were learning single imputation, and we started also with the case where only one variable had missing values, and then we said, okay, and now what should we do in case there are several variables with missing values? And we have seen back then that there are two approaches for the case where several variables have missing values. We can do the so-called joint model imputation, or we can do multiple imputation by chained equations, also known as the fully conditional specification approach. And we have seen in week 4 that the joint model approach is the original approach. So it was the first approach to be proposed for the case where several variables have missing values. And what it does is uh, it specifies a multivariate regression model for all the variables that have missing values, and the covariates in that regression model are the fully observed variables and all in our dataset, or other auxiliary variables that we might want to include for some reason, for instance, to make the missing at random assumption more plausible. But basically, that's what the joint model imputation approach does. For instance, imagine that I have three variables with missing values, and the three variables are continuous, so I can specify a model based on a regression model based on a multivariate normal distribution. But then if the number of variables with missing values increases, the model becomes quite high dimensional, and it's not easy to deal with so many dimensions. And also, most of the time, normal for continuous variables, normal models are used. Sometimes models based on the t distribution are used. There is software that implements this approach. But as I said, the main problem is when the number of variables with missing values starts increasing, then the model gets more and more complicated, at least from a computational point of view. And also, a further complication arises when we have variables of mixed type, variables with missing values of mixed type. For instance, imagine that we have one variable that has missing values and that variable is continuous and the other variable is binary or categorical. Then what is the model that we should use to jointly model these two variables? There are also methods for this case in the literature, but they are sophisticated, not easy to implement by ourselves, I would say. And so I will not cover this joint model approach here in this course. I'm just mentioning that it exists, so you know it exists. And I leave the reference to some softwares that implement this joint model approach in case you want to investigate. There are these three, at least there are more. Norm is the original one. It was proposed by Schaffer, and I think uh, it's implicit in the name. It rests on a multivariate normal distribution. Then cat is for categorical variables, mix is for mixed types, and then there is this JOMO. And there are more. These are, I think, the most popular ones. Okay. And our approach here, what we will study, is the so-called multiple imputation by chained equations or fully conditional specification. And this approach is nowadays often considered as the gold standard or the best approach to multivariate multiple imputation. And as you can guess, the mice package, what it implements, mice stands exactly for multiple imputation by chained equation. So the package mice implements this approach. And that's why we are using the package and covering this methodology here last week, because we only covered the case of univariate missingness, so there was no distinction between different types of approaches because we only had one variable with missing values. But when there are more variables with missing values, we know that we have two main routes, and we will follow this one um, that is widely known as mice. And basically, what mice does is that it imputes multivariate missing data on a variable by variable basis. And this requires the specification of a univariate regression model for each variable that has missing values. And so we reduce the multivariate problem to several univariate missing data problems. And this may seem that we are complicating our life unnecessarily, right? Because we are decomposing in the problem of multivariate missingness in a series of univariate missingness problems. But in fact, we are much more comfortable with univariate regression models than we are with multivariate regression models. And so this simplification or this decomposition, say, of the multivariate problem in a cascade, say, of univariate missing data problems, allow us to approach the problem in a much more flexible way, I would say. And why? Well, think of this toy example. We have several variables here, y1, y2, y3, y4, and some other variables as well, and they all have missing values, okay? And what mice does is, okay, I will impute the missing values on y1 using y2, y3, y4, and the other variables. I will impute the missing values on y2 using y1, y3, y4, and the other fully observed variables that I might have in my dataset, and the same for y3 and y4. So I specify univariate, multiple, linear or not linear. I specify multiple univariate regression uh, problems, models, sorry, not problems. And in this way, we can deal with variables of mixed type very easily, right? Because if y1, for instance, is binary, okay, I use y2, y3, y4, and the other variables as covariates, and I use to impute a logistic regression model, as we have seen how to do it last week. If y2 is continuous, then I also know what I can do, and the same for variables of other type, categorical, or yeah, categorical, binary, and continuous are the most common three types. And yes, this is how mice operates, but this is from a very high level perspective. Sorry, right? Because we know that all the variables have missing values, so we need to do something, right? Because I cannot just regress y1 on y2, y3, and y4, because as I'm seeing in this table, uh, they all have missing values. So what should we do? Well, the mice algorithm, or mice, is an iterative procedure, and using the toy example that we have in the previous slide, this table here, what mice does is, okay, I need to start um, by specifying regression models, and I need my covariates, or the variables that act as covariates in my regression models, I need them to be complete. So this is an iterative procedure, and what I do is I will use some starting values to initiate my procedure. So I will, for instance, imagine that I'm interested in imputing y1 uh, given y2, y3, y4, and the other fully observed variables, y2, y3, and y4, they have missing values. So what I can do is, to start the procedure, I impute the missing values, and also on y1. So I impute all all missing values in all variables in a very naive approach. I can use min imputation, for instance, and we know that min imputation is bad, or I can just use like a random draw from the observed data for the different variables, a random draw from the values in y1 for imputing the missing values in y1, and the same for y2, y3, and y4. And by doing this naive step, I no longer have missing values. But okay, I know that what I'm imputing, it's not it's not of any value, say, or it's not good, because I'm using mini puntation or random draws from the observed data. So I know that this is just to start the procedure. And then, okay, I have already some initial guesses for the missing values, and I will use the regression model that I have specified for y1, and now I can use y2, y3, and y4 because they no longer have missing values. And I also use the other observed variables in my data set. And this is the step that I'm doing here. Then I go to y2. I do this in a sequential manner. Then I go to y2, and I will use y1, but for y1, I'm not using the initial guess because I have already updated y1 in the previous step. So in the regression model for y2, I'm using the most updated value from y1, and for y3 and y4, I'm using the initial guesses. Okay, and I also use the other variables in the data set in case they exist. And I keep doing like this, right? Then I go to the variable y3, and I use the most updated values of y1 and y2, and the initial guess of y4, and the other fully observed variables. And then I go to y4, when I go to y4, I already used the most updated values for y1, y2, and y3, and then I complete. I have gone after one iteration. I have gone through all the 4 variables, and then I repeat. I go again to y1, and now to impute or to update y1, I use the values for of y2, y3, and y4 from the previous iteration, and the same for y2, y3, and y4. And I repeat this, I loop, let's say, until conversions. And at the end, at conversions, so basically in this case, for the 4 variables, right? And each of the 4 variables, they might have several missing values. For instance, here in this toy example, y1 would have 1 missing value, y2 1 missing value, y3 2 missing values, and y4 2 missing values. And I do my iterative procedure for, say, a number of iterations, and then I have several imputed values, right? And what I use to impute the values in my original data set is the values from the last iteration, okay? The most recent values of y1, y2, y3, and y4 on the most recent values imputed on these variables, okay? And then I use these values from the last iteration to replace them in my original data set. But note that I do this iterative procedure, and this only leads to one completed dataset. But in the context of multiple imputation, I'm creating M capital copies of the dataset, and then I need to repeat this procedure M capital times. I need to repeat the procedure as many times as copies of the dataset that I have created. And just to think, this is a kind of an aside, but I think it's important. Mice multiple imputation by chained equation, the algorithm or the procedure. Then mice is also the package, but here mice, the algorithm or the approach, is a Markov chain Monte Carlo method, and it's based on the idea of Gibbs sampling. And now you are asking, okay, MCMC, Gibbs sampling, what is this? Those doing Bayesian theory, you should already, I think, by this week, to be familiar with these concepts, and make we will make use of them in practice because we use the mice package, and the mice package is what it implements. But I just want to pass the main idea. And MCMC, Markov chain Monte Carlo, is a technique that allow us to draw samples from a complex distribution. It's heavily used in Bayesian statistics, but it's not necessarily a Bayesian technique. We have a multivariate distribution, say, and we want to draw samples from that multivariate distribution, and we can use MCMC. Then that multivariate distribution can be our posterior distribution in the case of Bayesian statistics, but it doesn't need to be. So it's not specific to, or it's not some. It's used in Bayesian statistics, but it has a broader scope. And MCMC works by creating a chain of random variables, a Markov chain, and the distribution that each element in the chain is sampled from depends on the values of the previous element. You can see now the parallel to what mice is doing, right? Because we have several variables, and we are sampling or imputing. So to impute, we are sampling from our imputation, from our univariate imputation regression models, and we have just seen it depends on the values of the other variables, and it is done in a sequential manner, and it depends on we are drawing, for instance, in the case of y1, we were drawing from its imputation model that depended on y2, y3, y4, and the other variables, and we use the most updated value. So this is a kind of the Markov chain idea behind mice, and under certain conditions, the Markov chain of the draws that we are making will eventually get stable, and it can be proved that samples from the chain are then samples from our complex distribution of interest. So this is the main idea behind mice. But more specifically, mice is based on the idea of Gibbs sampler, and Gibbs sampler is a particular MCMC techniques that allows drawing samples from here. I need to correct, it's not. It allows drawing samples from a multivariate, sorry, distribution by splitting the multivariate distribution into a set of univariate full conditional distributions. So basically, if I'm interested in the conditional distribution, I use F of y1, y2, y3. This is my multivariate distribution of interest, and what Gibbs sampling does is I will decompose this in the following conditional distributions. Okay, and it can be shown that a sample of the multivariate distribution of interest can be obtained by repeated sampling from each of the univariate conditional distributions. So if I sample from this distribution, this distribution, this distribution, if I do this in an iterative way for long enough, it can be shown that I'm drawing from this distribution of interest. And that's the main idea behind mice, and I will come to this idea of Gibbs sampling in some minutes. And okay, basically, mice is an iterative procedure, right? And for each variable, we might have several missing values, right? And we are imputing them and we are cycling, right, until convergence. And so for each imputed value in each variable, or for each missing value in each variable, we have a chain, right? Because we repeat the procedure uh, several times, and so we are imputing several times for each variable and for each missing value. So at the end, for each missing value, I have a chain. In fact, it's a Markov chain, but I have a chain. Okay, and uh, why do we need to iterate? Well, because we have seen that the procedure to start, we use some initial guesses or mean imputation or random draws, and these initial guesses that we are using to impute the values, they might not come from our distribution of interest, right? And so they are possibly not coming from our distribution of interest, but they can be far away, and so possibly the very first few iterations of the algorithm, we are not sampling from our distribution of interest in the context. And remember that mice is based on the idea of MCMC, and so basically we are not at the stationary distribution, and that's why we need to iterate. And so here it's important also that we monitor the convergence of the chains of the imputed values. But think that in practice, we might have several variables with missing values, and the number of variables with missing values may be large. And then for each variable with missing values, we may have several missing values. So remembering that for each missing value, we will have a chain of imputed values if we want to monitor the convergence. So we have a lot of chains to look at. right? So basically what I want to look at, and for those doing Bayesian statistics, you are already familiar with this concept, but I want to look at, I will have a plot of the iteration number against the imputed value. And my chain can look something like this. But remember that if say that I have 5 variables, well, less, 2 variables, y1 and y2, and I have, say, 5 missing values in y1 and 4 missing values in y2. So I will have 5 chains to look at y1, 4 chains to look at y2, right? But then I have as many chains as also copies of the data set that I'm making, right? So if I have made 5 copies, for each copy of the data set that I have made, I will need to look at all of these chains. So it's infeasible that, and in practice, we know that we usually need a quite large value of m, and we have seen uh, or we have touched this issue already. So the point is that it's infeasible to look at the chains of the imputed values for all the variables, for all the copies of the data set that we are making. And as an alternative, and this is what is implemented in the mice package, what we look at is mice, what it does is, okay, for the sequences for each variable, I will look at the mean of the imputed values by iteration. So at each iteration for on the example of y1 and y2. So on y1, I look at for each iterations. Remember, I had like say 5 missing values rather than looking at the chain of all the 5 missing values. What I do is that by I look at the chain of the mean and the standard deviation. So I don't need to look at 5 chains, I look at 2, and the same for y2. And of course, this leads to huge savings when I have several variables and many missing values. And I look at the mean and the standard deviation, for instance, of the chain of the imputed values for each copy of the dataset that I have made. And I'm saying the mean and the standard deviation, we can use other summary statistics. This is what comes by default in the package mice. You can customize to look at different summary statistics, but in general, it will be fine. And the good thing is that typical applications of MCMC, they require iterations on the order of thousands of iterations. And here, because this is a kind of different application, it's an application of MCMC, but on a very different context. Here, the number of iterations that we need to reach convergence is typical and fortunately much lower. The default for the number of iterations, so the number of times that we are cycling, imputing from the different for the different variables and cycling, the default in mice is 5. I would say that 5 is a kind of low or very low. It might work well, but if we then want to look at trace plots, at plots of this for the mean and for the standard deviation, it's kind of difficult to judge conversions based only on 5 iterations. So in practice and to judge conversions properly, I would suggest 20 or 30 iterations so we can have a better idea. And basically, when we look at the trace plots or the plots of the summary statistics against the iteration for each of the copies of the data set that we have made, what we do not want to see is some trends, okay? And this is 2 examples of trace plots. This is from the book from the author of the mice package, The Flexible Imputation of Missing Data. And here we are looking at the mean and standard deviation. This is the typical output from the mice package. And this is an example of trace plots of chains that have converged and are mixing well. And then remember that we take the last value here, not the last value here and here, because this is the mean and the standard deviation. But if it was the imputed values, we would pick up the value from the last iteration. But Here, everything looks fine. But again, if I only use 5 iterations, it's kind of difficult to know where the chains are mixing, sorry, well or not. And here, this is the typical example of problematic convergence. So they are kind of getting stuck at some points, and we will see in the practical typical examples of not well specified imputation models that might lead to this. But here the point is just we should expect to observe something like this. Okay, and this is for the convergence, and it's important. Why? Because if chains have not converged, then we will all our results, then we will use the values from the chain to impute the missing values, and then we use those data sets to do our analysis. And then if the chains have not converged, so I cannot really trust my results, they can be wrong. So it's important that we monitor convergence. And going back again to the fact that mice uses or mice is an MCMC type of algorithm based on the idea of Gibbs sampling, and I've already mentioned what Gibbs sampling for a multivariate distribution, right? Fy1, y2, and y3, and we are interested in that multivariate distribution. And what we do is that we work out the full conditionals, the conditional distribution of y1 given y2 and y3, of y2 given y1 and y3, and of y3 given y1 and y2, and we sample from those distributions, and we know it was shown that this corresponds to sampling from our multivariate distribution of interest. But mice works exactly the other way around. Why? Because we start specifying our regression model. So if we have 3 variables with missing values, we start specifying what is the regression model for y1 given y2 and y3, for y2 given y1 and y3, and for y3 given y1 and y2, right? We do not start from a multivariate distribution and then we come up with the full conditionals, but we do the other way around. We start with the full conditional distributions, and then we somehow cross our fingers and hope that there exists a multivariate distribution that corresponds to these conditional distributions. And this leads us to the concept, and we have superficially approached this in week 4 of the concept of compatibility. And here I need to correct this as well. Two conditional densities fy1 given y2 and f of y2 given y1 are said to be compatible if a joint distribution fy1 y2 exists such that it has fy1 given y2 and f of y2 given y1 as its conditional density. So basically two conditional distributions are said to be compatible if it exists a joint distribution of that variables such that the full conditionals are those exact conditional densities. And the problem with mice is that by specifying separately the conditional densities, right? What we are when we specify a normal regression model, it's a normal distribution, say for y1 given all the other variables observed or not. So there is no guarantee that by starting by specifying the conditional distributions that there exists a multivariate distribution that corresponds to those conditional distributions. And is this a problem? Well, some say yes, some say no. Van Buren, the author of the book, we need to interpret this with some grains of salt because he's also the author of the mice package. He says on his book that though mice is only guaranteed to work if the conditionals are compatible, these simulations, it was from a paper, suggest the results may be robust against violations of compatibility. And he also concluded the discussion about compatibility in his book on the page, I think was the next page, 124, saying, apart from a potential feedback problem, we will look at a feedback problem. We will see what it is in the next video, but it arises from regression models or imputation models that are not well specified, it appears that incompatibility seems like a relatively minor problem in practice, especially if the missing data rate is modest and the imputation models fit the data well. So there is still some hope that even if our models are not compatible, that this will not be a disaster for our results. And I will not cover or illustrate it, but there is at least a couple of packages that use mice ideas, and they try to correct for this compatibility problem that might arise, but it starts getting too technical and is out of our scope here. And finally, we have also seen, I think, 2 weeks ago in week 8, we first when I first introduced multiple imputation, we have seen the concept of congeniality, right? And I think I've mentioned that it's a concept that it's often confused with the concept of compatibility. They are kind of connected, but they are not the same. So compatibility refers to the property that the conditionally specified models together specify some joint distribution, okay? And is a theoretical requirement of the Gibbs sampler. And congeniality refers to the relation between the substantive model, our model of interest in step 2, and the imputation model. And it's kind of widely accepted that our imputation model should be more general than our substantive model of our analysis of interest. So if we have, for instance, many variables in our data set, and if our analysis just, for instance, uses 2 or 3 of such variables, we should make use of the other variables as auxiliary variables in our imputation models, not only because it helps the missing at random condition to be satisfied, but we can also gain some precision in our imputed values. And also, for instance, if our uh, model of interest, if it contains like interactions between variables or quadratic terms of some variables. For instance, if I'm interested at the effect of age and also the square effect of age, then these effects should also be reflected in our imputation models. And that is where mice starts getting some problems, because by default mice assumes that all relationships are linear, okay? And so if we then have some nonlinearities due to interactions or quadratic terms, it's not always clear what we should do with mice, the algorithm, but also the package, in order to get reliable estimates. And that's mainly it from the theoretical or methodological concepts of mice multiple imputation by chained equation. So it's for the case where we have several variables with missing values. What we do is that we decompose the problem of multivariate missing to a sequential, to a problem of specifying in a sequential manner several univariate missing data problems. So we are back to what we have learned last week in terms of what models are available. Then it's an iterative procedure, right? Because several variables have missing values. They are used as covariates in the other imputation model. So I need to do some random draws or use some initial guesses, and then I need to iterate until I get values, or I'm sampling the values from my distributions to impute, and there I need to repeat until they get stable, right? And then we have the concept of compatibility, that we are mice is based on the idea of Gibbs sampling, but on the not in the usual way. We don't start with the multivariate distribution and we go to the full conditionals. We start the other way around. We start with the full conditionals and we go to multivariate, and there is no guarantee that it will always work. And then we have the concept of congeniality, that basically refers to the relation between the imputation model and our substantive model of interest. And just to finish, mice is great, and I think it's a very good package. I think that's why we are learning it in terms of package methodology, and then the package, because the package has a lot of functionalities, and sometimes we do not appreciate, but someone had the work to code everything and make it available, so we should recognize that. And just to finish this part, the assumptions that mice, the algorithm, makes is that the missing mechanism is missing at random or missing completely at random. All associations between the variables are linear, and we have the concepts of compatibility and congeniality. Okay, and that's everything for this part. We will now look in the second video for a tutorial in our implementing or practicing these concepts. Okay, see you in the next video. Thank you.